Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is July 5th, 2016. In this video lecture, we will be discussing the true power output of the turboshaft engine, a pure torque application driven by the turbine engine core. In this particular application, we must focus on a non-aerospace application for which the turbine engine is used only for shaft horsepower, devoid of any hot gas thrust propulsion. So focus on the exhaust part of the free turbine on a turboshaft. That would be a divergent nozzle so that the pressure does not turn into velocity. So you get a lot of slow moving heat out the exhaust. But again, all turbine engines have a gas producer with a set of compressor blades in the front connected to a set of turbine blades in the rear. In between the compressor and the turbines is a combustion chamber, and that combustion chamber has dilution holes and airflow mixture and all that stuff for cooling and mixture. So once the gas producer starts up, it's going to draw the air in, compress it to heat of air compression, mix it with the kerosene, ignite it, and then blast it against the high-speed turbine, which is going to then keep the compressor running for the heat of air compression, which then has a sufficient temperature to keep the fuel ignited. Then you don't need the starter or the spark, much like diesel heat of air compression. And then what you do with that hot gas velocity is you channel it to a second independently rotating spool with compressor and turbine blades, and that thermal energy is then converted purely into shaft horsepower. So you can imagine the amount of pressure going on, just like the diesel piston. There's so much pressure going on the absorption structure, in this case a turbine, not a piston, and it turns it into a high amount of shaft horsepower in the form of torque and RPM. Then whatever you have in the form of brake horsepower, which is a function of torque and RPM, you can then step it down into a gear reduction unit, which can then power an AC generator, like the turbine electric systems on some trains, or you could use that for electrical power generation at utility companies. But the idea is how much airflow you can draw in. Now, you don't want too much with a turboshaft. The amount of mass airflow might be no more than 30 to 40 pounds per second, and there's no oncoming airflow moving into the intake, right? It's set up for shaft horsepower only. So you have to pay for compressing that mass of air and increasing its temperature. The BTU is the increase of a mass times its temperature rise. So you lose that to keep the compressor running. But whatever you get after that, because the pressure's high enough, you can then channel to a free turbine, which then is connected to a gearbox for gear reduction. And then you have a pure torque brake horsepower application run on turbines, not pistons. So a common application would be power generation, Siemens turboshaft, gas electric operations. They produce a whole lot of power with relatively small and lightweight operation. And then you can also take that waste heat and channel it to a heat exchanger and use that as a boiler. You can use that also for supplemental power elsewhere. You can also bleed some of the cold air compressor flow to run air conditioning system, high-low pressure exchange. So you got a whole HVAC system too. And that's with any gas turbine engine. You can do that. But, if you're on the ground and you have all the surplus power after running the application, you can also use that for other amenities. So the turboshaft non-aerospace ground application becomes very valuable for commercial applications of power generation, water flow, you name it. And then you can run that at constant speed around the clock. On a maintenance level, you need to periodically shut down the engine and do a borescopic inspection, as with any gas turbine engine. But the idea is that you have a very reliable source of power, lightweight, high power. And the turboshaft, again, is the same thing as any other turbine engine. It's just what you do with that thermal energy output. And again, you're running about 20 to 25% thermal efficiency on the typical turboshaft application. And if it's at constant RPM, consistent horsepower output with a governor on it, then you can have reliable electrical power from a utility station. So that's the advantage of the turbine engine for shaft horsepower, which is very closely related to the diesel piston engine because it's all heat of air compression. But still, even though the diesel piston engine is close, it still has a lower power to weight ratio than the turbine engine. So if you can get into the turbine engine application of shaft horsepower, you can use a relatively lightweight, smaller power plant to get a lot of power, as in compared to a piston engine, because it's high pressure against a turbine instantaneously getting RPM and torque versus the locomotion that you get in a piston engine. But the piston, of course, is very practical for high acceleration, stop and go driving. So yeah, that's why you don't see the turbines on the cars. But Chrysler used to make a turbine engine for the car in the 50s. And, they had a little problem with overheating. And like the diesel, you have to move the oil around to a cooler. And it just wasn't really practical. But today, maybe with the materials and the computers out, they could bring back a turbine-powered flywheel in a car. And that's just an example of a turboshaft engine. Common turboshaft engines are the Allison 250 C30, now owned by Rolls-Royce, which was once a Detroit diesel Allison application. And of course, the Siemens turboshaft turbine electric power plants are very popular, and a lot of big corporations use them for power generation. So that's the true power output of the turboshaft engine and its similarities to the other types of gas turbine engines. Thanks for watching this video, and have a great day.